All right, welcome everybody. So we have made it to the zenith of a first year single variable calculus sequence discussion of Taylor series. We've actually seen Taylor in some form or fashion previously with Taylor polynomials, where we were utilizing derivatives of a function evaluated at a particular point, dividing by n factorial to cook up the coefficients that go into a degree d Taylor series. So if our degree d Taylor polynomial. So if we were writing this Taylor polynomial maybe in sigma notation, we'd have some, n equals 0 to d of c sub n x minus a to the n. And this is the form of our Taylor polynomial. Well, if you take a Taylor polynomial and you just don't, well, what we saw, I guess, with Taylor polynomials is that the higher the degree, the better the approximation, right? You go out to degree 1, you get a tangent line. You go out to degree 2, a tangent parabola. You keep increasing the degree, you get a better and better approximation. Well, what if you just didn't quit? What if the ... just didn't stop? Well, in this case, you would have a Taylor series of f of x at x equals a. And here to write this out, it's a very similar expression in terms of the summation, but now the sum goes from n equals 0 to infinity. And the idea here is now you don't just have a good approximation or a very good approximation, you have the best approximation. You really almost can't do better than a Taylor series in terms of trying to approximate a function. And boy, the expression that comes out, as we saw sort of in the last section, is just so smoothly differentiable and anti-differentiable. So I'm going to pause here, show an example, and then see how that example can sort of benefit us in practice. All right, so let's work through a computation. We're going to find a Taylor series of f of x equals e to the x at x equals 0. And so if you're going to compute a Taylor approximation, what do you start doing? You start computing derivatives. Well, the derivative here is e to the x. The second derivative is e to the x. In fact, even the nth derivative is just e to the x. Now we can take this expression for the nth derivative and utilize it to cook up our coefficients. So this nth derivative expression, let's evaluate it at our center, x equals 0. So evaluating at our center, we get the nth derivative evaluated at 0 is equal to e to the 0, which is 1. Okay, great. What do we do with this now? Now we take this and we divide by n factorial all the way through, and we get 1 over n factorial as the value for our c sub n. So this is the c sub n within our Taylor series. And so whenever we're looking at our Taylor series here, the Taylor series for e to the x, sum n equals 0 to infinity. The c sub n here is just 1 over n factorial. And then we have, x minus a to the n, which in this case would be x minus 0 to the n, because we're centered at x equals 0. But of course, x minus 0 is just x. And so there we are. There is a Taylor series for f of x equals e to the x. That is the best approximation of f of x equals e to the x that you could get by leveraging derivative information, because you are not only using the first, the second, the third derivative, you're not only using the 100th derivative, you're going all the way out infinitely many derivatives deep. There's no more, you sort of can't go deeper than that whenever it comes to computing derivatives. Now, what's interesting about this, this function that results, if we tried to compute the radius of convergence of this Taylor series just to see on what interval this Taylor series would be approximating our function e to the x well, we could compute that radius of convergence, by taking a limit as n goes to infinity of, replace n with n plus 1, you'd have 1 over n plus 1 factorial x to the n plus 1 all over 1 over n factorial x to the n. And we want this to be less than 1. Now the x's cancel nicely. We've seen this a number of times when working with the power series. We have x to the 1 upstairs. And then you could factor out an x from your limit. And when you would, you'd then have what? Just limit n goes to infinity. I guess we could flip the n factorials as well. And we get n factorial over n plus 1 factorial. But hey, that cancels kind of nicely too, right? Because and we want this less than 1 for convergence. The n factorial cancels with n plus 1 factorial. All of the n factorial cancels. You get just n plus 1 downstairs. And so whenever you would reciprocate this to get your solution for x, you'd have absolute value of x is less than, bring to the other side, reciprocate, you'd have limit as n goes to infinity of n plus 1, but that is infinite. And so what that says is this Taylor series actually has an infinite radius of convergence. The radius of convergence is infinite, and so this series should give us a fantastic approximation. In fact, it's going to give us e to the x for every x. So this expression is just really the e to the x function. And if you take a look at this and you start running derivatives, you could actually see why this would make sense. Just to show you here, what if you took t prime of x? You would just use the power rule, right? That's one reason why power series are so straightforward with respect to calculus. You bring the n down, but hey, when you bring the n down in front, it's going to cancel with that n factorial downstairs. Oh, excuse me, we got to go from n equals 1 to infinity here. Bring the n down, and then it will cancel with the n factorial, and then you'll just have n minus 1 factorial remaining with x to the n minus 1. And actually, look how this takes almost the exact same structure. In fact, if you re-index this, you could see that this is identical to sum n equals 0 to infinity of 1 over n factorial x to the n, because here, if you start with n equals 1, you'll get 0 factorial x to the 0 as your first term, which is exactly what you get here. But please observe, these two things are exactly the same. And isn't that the nature of the exponential function, right? It is its own derivative, and that's exactly what we're seeing here. So the Taylor series is inheriting properties from the function that we have known previously. The Taylor series is expressing the function in a really a new form. But if you ever wonder, like, how does a calculator compute e to the 1.2 power? Well, it uses a Taylor series, of course, because that's the way that we can sort of naturally compute with the expression of e to the x. I got one more thing I want to touch on related to this, which will ultimately bring us back to series, utilizing the result that we just got here, and then that'll sort of put a bow on what we've done with Taylor series. All right, so let's take a look at a couple examples here. So here's a fun one. What if you want to add up 1 over n factorial for n equals 0 to infinity? So this is essentially what, like 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, ... Now, if you run a ratio test, you will get that this series converges. But what if we didn't just want to know if it converges, but to what value it does converge? Well, as it turns out, we could think of it in terms of the Taylor series of e to the x. Check it out. If we just replace x with 1, you'll get exactly this. So this is actually exactly just t of 1, because t of 1 would be sum n equals 0 to infinity of 1 over x to the n, 1 to the n. But 1 to the n is just 1, and so, well, that does it. But t of 1 here is evaluating the exponential function at 1, which is just e to the 1. And so, in fact, this is just an expression for e. Okay, not too shabby. Hey, what about this next one? We've got sum n equals 0 to infinity of 4 to the n over 7 to the n n factorial. Sum n equals 0 to infinity. Well, hey, this looks a whole heck of a lot like the Taylor series as well. This is actually one I recall working through on our WebAssign discussion. Well, here we're not replacing x with 1, but we're replacing x with 4/7. Note, this is just t of 4/7, because that's going to be what? Sum n equals 0 to infinity, 1 over n factorial, 4/7 to the n. That's going to put a 4 to the n upstairs. That's going to put a 7 to the n downstairs. And how is this going to evaluate? Well, t to the 4/7 is the Taylor series for e to the x. It had an interval of convergence that was infinite. And so, hey, this is just e to the 4/7. Nothing more than that. Yeah, so not bad, right? I mean, this gives you, this sort of hints to, it doesn't show like the full power, I suppose, of Taylor series, but it sort of hints to the fact that once you have a Taylor series in hand, my goodness, the things that you can do with it are numerous and potent. And they are just fantastic expressions in terms of their ability to be differentiated, to be integrated, to be evaluated. It's just a world of possibilities. And yeah, once you have a Taylor series, you just really peer into the machinery of the function itself, and you really just get to see the inner workings of how it functions. No pun intended. So I hope this was an enjoyable video, and I hope this sort of gives you some insight to how Taylor series are just one heck of an idea to have in your brain now moving forward through life.